Everything's going well. Homeworks are all right. Hope you're learning something useful, something that'll help you, with your own data analysis and with your own research. So today we're going to learn another, I think, useful thing, which is how do we classify things when we don't have labels. So we're going to learn two algorithms. One is called k-means, and the other one's called expectation maximization. And our problem, the homework that you're going to have tonight, is to classify an image. So it's a brain image. It's an image that was taken, I think it may be my brain, I'm not sure. Probably have a few holes in it. Anyway, what you need to do is to classify the brain regions into white matter, gray matter, and outside the brain. So three clusters. And you're going to do it using EM. And the idea is really as follows. So what you have is that you have some space of data. Call it, x1 and x2. And you have some data points there, like this. And they're not labeled, so you don't know what belongs to what. And what you hope to do is that you hope to, label that data so that when you look at it, you say, well, actually, these data over here are from class A, and then these data over here are from class B. So you want to get labeled data, even when there are no labels. And so for your homework, what you have is that you have some image of the brain, some part of the brain. You think it's like a slice through the brain like this. And if you look at that slice and you just do a histogram of the values. So you have some pixels, and then you have some value at each pixel. And you look at that histogram, you might see something like this. And so you have some distribution. So this is the histogram, so the number of pixels. And based on this, which is the only thing you have, you want to know, can I classify the data that I have into things like gray matter, white matter, and air, for example. And the kinds of algorithms that we're going to learn are going to be the mechanisms by which one does classification when there are no labels. And like always, we're going to use a probabilistic approach where we are going to have a model that says this is how we believe our data was generated. And once we have a generative model, then we're going to say, given this model, then how do we find the maximum likelihood for, the labels? What's the probability of this data point belonging to class A, class B, or so forth? So the basis of these models are mixtures. And let me describe to you what are mixtures. So mixture models. And basically the idea is that you start with a particular belief that there are exactly M classes in the data. So you may not know that a particular data belongs to whatever class, but you start with saying, I believe there are three things that I want to label. White matter, gray matter, air. So those are the three things that I want to find. So that's the first thing. The second idea is that your labels And so here, so this is y is my label. It belongs to some class. This is my range. And the second thing that I know is that each class has a probability. So there's some probability that y is equal to I. This is the prior probability, right? That you have some prior probability that each class is going to have, with some probability, is going to appear. And then you're going to have a likelihood. So what's P of x given y? So given a class, we know the distribution of the data from that class. So in a mixture model, what you're saying is that your data, which is all you have is your data, right? You have P of x. This is what I plotted here. This is P of x, right? This is just the probability of my data. In a mixture model, what you're saying is that that P of x is generated by my class. So I have m classes, and I have some probability of x where y is equal to I times the prior probability. So this is my mixture model. This is your data. So if you look at this equation, it's saying that this is what you have. And look, you don't know this, and you don't know this. These are the things you want. But if you could get these things, then you could say, what's the probability of y being equal to I given some x in trial, I or m. So I have some data, x. What's the probability of it belonging to class I? That's what I would like to be able to estimate. And this is all I have. I just have data. But the mixture model says your data was generated by this process. And so this is where we're going to begin with. And so, for example, let's give you an example of how this might work. So suppose that we have the likelihood P of x given that y is equal to I is some normal with mean mu I and variance sigma I. So I have my likelihood. Suppose that it's a normal with this mean and this variance. And so in my model, I have these parameters. My likelihood model, my mixture model, has some parameters in it. And what are those parameters? Well, I have the prior probability of y being equal to class 1. I have the mean of that class. I have the variance of that class. So I have the mean and variance, and I have the prior probability. And then I have that for the second class. I have the prior probability of y being equal to 2. I have the mean of that class, and I have the variance of that class. And then if I have 3 classes, I'm going to have prior probability of being in the third class, the mean of that class, and the variance of that class. So these are the parameters of my generative model. If I knew these parameters, if I knew what these things are, I would say that that's what generated the data that you have. Of course, I don't know these parameters. So if you only have 3 classes, my generative model is that there's some parameter y that generates some data with mean mu1, variance sigma 1, would mean mu2 variance sigma 2, that would mean mu3 and variance sigma 3. So this is how my data was generated. And what I have is just P of x. And so if I were to label my data, so my first data point, perhaps I would say, if I could label that, I would say maybe it's class 2 or so forth. X2 is class 3. X3 is class 1. So if I could label them with my parameter, with my vector, with my variable y, this is how I would label them. And that's what I want to do. I want to be able to label them like this. Now, in k-means, so we're going to look at two algorithms today. K-means gives you one class per data point. But with EM, we get a probability of a class for that data point. So we're going to start with k-means, and we're going to see how k-means works. Once we understand k-means, then I think EM is a little bit easier to understand. So the first step along the path is that let's imagine, instead of having y being these classes, let's make a random variable z that is going to have the following value. So when it's a 2, this vector z is going to be a 0, 1, 0. When it's a 3, it's going to be a 0, 0, 1. When it's a 1, it's going to be a 1, 0, 0. So not a binary, not the way we would think about a binary vector, but z can take a value of 0 or 1, and if the second element in my z vector is a 1, then I'm going to say that's class 2. If it's a third vector, third element of the vector is 1, I'm going to say that's class 3. If the first element of the vector is 1, I'm going to say class 1. So I wrote it this way. It's a little different than the way you would obviously write it if you were doing binary coding, but don't be confused by that. All I'm saying is the z is a vector random variable, and depending on which element of the vector it's 1, that's the class that you're going to label it. That's all I'm saying with it. Is that clear? I don't want you to get confused by that. Make sense so far? Okay. All right. So you have some, I'm going to replace this with this now. I'm going to say there's some hidden variable z that's going to generate, which I don't know what it is, but it's going to generate some x. And I've measured x. I just don't know what z is. And so my mixture model is that P of x is the sum of I is equal to 1 to 3, P of x given that z sub I is equal to 1 times the probability of z of I equal to 1. So that's how I believe my data was generated. So we're going to begin with k-means. What we would like to have is that we have a classifier. So our classifier is that z sub I for data point n is 1 if x of n is class I, otherwise z sub I of n is equal to 0. So our nomenclature. Z sub 1 is 1 if x of n is 1, otherwise it's 0. Okay, so now what we need to do is to describe the mean and the variance of each class. So we have whatever number of classes, they're going to have some likelihood. That likelihood is going to have a mean and a variance, and so we're going to need to know what's the mean and variance of the data for class 1, for class 2, for class 3. Of course, nobody's going to label it for us. We're going to have to label it ourselves. But if we had the labels, if we knew what class each data belonged to, we should be able to describe the mean and variance of it, obviously. So what we do is that we say, okay, let's count the number of times a particular class was present, which means that n sub j is going to be the sum of I is equal to 1 to all the data point n of z sub j of I. So basically saying, you know, how many data points you have labeled class 1, how many data points you've labeled class 2, how many data points you've labeled class 3. So if you had the data already labeled, this is how you would be able to count the number. And then there's a mixing proportion. Which is the probability that z sub I is equal to j. That's equal to nj divided by number of data points. So the probability, the prior probability of a particular class is the total number of data points that were assigned to that class divided by total number of data points. Okay, so what am I doing? I am trying to get the things that I need to get this P of x. And if I had my data labeled, then this guy here would be the number of data points that were labeled for that class divided by total number of data points. Now I'm going to have to find this probability distribution. If a particular class is the label of this data point, what's the likelihood of that data point? Well, I'm going to have to find its mean and its variance. So I'm going to look now, find all the data that belong to a particular class and find its mean and variance. So mean of each class. Well, that's just mu for class J is 1 over the number of data points that are in that class times the sum of I is equal to 1 total number of data points of that z sub j of I, x of I. So take all your data points, multiply it by whether it belongs to a class or not, sum it all up, divided by the total number of data points that belong to that class, that's the mean of that class. And then variance of each class. So if your data was labeled, then you could find the prior probability of a particular class, the mean of that class, and the variance of that class, and that's how you would do it. All right, but your data is not labeled. So what does k-means do? So k-means starts by an initial guess. About the mean mu j of each class. So you just pick a random location for each class. Say you have 3 classes, you say, okay, I'm going to pick this place to be the mean of this class, this place to be the mean of that class, and the third place to be the mean of the third class. That's just, I'm going to do it randomly. Then what we're going to do is that if I have the mean, then what I can do is say assign each data point to the class that has the closest center. Right, so you can do that. You can find the distance of every data point to that center, and that going to say, okay, whichever center you're closest to, that's the class that you belong to. So now you've labeled every data point, right? So if you've labeled every data point, that means that you can go and re-estimate the mean and variance and the prior probability, which is what we just did up here, which is this. So if I have labeled every data point, then I can do this. So I start with a random center. I assign each data point to the class that has the closest center, and the second step is that I re-estimate the class center. So I re-estimate mu j. And that's it. That's k-means. It assigns data randomly to begin with. It finds the one that's closest to that center. Then it re-estimates the center. And then it keeps on doing it. Goes back and says, okay, well, if these are the clusters that, if this is the data that belongs to the center, what's its mean? The mean is going to move from the random position to someplace else. Then you're going to ask again, who gets to be in this class? Again, based on their distance to the new mean that you have, you get a new label, you re-estimate its mean, and then you get finally the mean moves to some location, and then you have your labeling of it. That's called k-means. The cost that you're minimizing is this. Which is number of data points then you have classes So what you're doing is that you first guess the center, mu j, for class j, then you assign which class it belongs to based on the points that are closest to that center, and then you calculate a new center, and then you go back and do this again. Okay. So k-means does hard membership. You belong to the closest center, and you get a number that says, you know, for every data point, this is the class that I belong to. So k-means has hard membership. We get something like, looks like this. What EM is going to do is going to do a probability for the same problem. So we're going to have x, we're going to have x1, and we don't know the class. But what we're going to do is we're going to assign a probability that z class 1 is equal to 1 given x1, the probability that z2 or the probability z3. So we don't want to know this. We want to know what's the probability that you're class 1 given the data point x. Okay, so we want a soft classifier. We don't want a hard classifier. And that's what EM is going to provide us. And it's a powerful algorithm. It's going to allow us to do lots of things. But we're going to begin with this, with our problem of trying to classify unclassified data. So this probability that zi is equal to 1 given x. So we know that that's depends on the likelihood. And the prior divided by a marginal. P of x, our data, which, of course, that's what that is just if there are m classes, that's the likelihood times the prior probability over all the classes. So what EM does is that it divides the problem into two parts. In the expectation part, what it does is that it says, well, imagine that you have all the parameters of your generative model. You have the likelihoods, you have the prior probabilities. If you had that, then what's the probability of this class given your data? It assigns for you based on the notion that you have the generative model, the label. Just like in k-means. So in k-means, we had this heuristic. The heuristic of k-means was which center are you closest to? Let's assign you to that class. In EM, we say, what's the probability of you being in a particular class, assuming that you have the generative model, you have the way you thought the data was generated, you had the mixture. If you had those parameters, if you knew the means and the prior probabilities, you should be able to assign your data. But your assignment is going to be soft. You're going to describe a probability. Once you have the probability, that's your E step. Once you have the probability, then you have the, based on that probability, you can get to the M step, which is to say, well, what's this generative model that produced this data? If I have the labels, if I have labeled my data, can you tell me the mixture model that would have produced this label? And so that's the process, which is, in a way, in my opinion at least, similar to k-means, but it uses probabilities, not hard, labels. So let's see how it does it. So similarly, we're going to begin with class membership. So if we had our data labeled, then we would have something like this. Where I'm going to have some variable I'm going to call tau of j of data point n. That is going to be my probability of I'm going to be class j given that data point. So this is what I'm after, right? I want to label my data points, and if I had them labeled, I'm going to call that tau. So instead of before, so if you look at what we did with k-means, we said now next is count the number of times a particular class was present. Well, that's just the sum of z's. But now my membership is soft. So number of times a class is present is n sub j. That's the sum of I is equal to 1 to n of tau j of I. So it's sum of these probabilities. This number of times you've seen a particular class. Then your mixing proportion, which is your prior probability. Prior probability that you're going to get a particular class is nj, how many data points you labeled for that class divided by total number of n. And of course, n is not going to be an integer, right? It's going to be some real number. Then the mean of each class mu sub j is going to be 1 over nj weighted sum of my data, where that weight is the probability of it belonging to that class. That's the mean of that class. And then variance of each class is this. So if I had my data labeled, if I knew what probability of z was given x, then I could compute all of these things. I could compute the elements of my mixture model. So what EM does is to say, start with step 0, just guess the parameters that you need. Which are theta, the prior probability for class 1, the mean of that class, the variance of that class, the prior probability of class 2, the mean of that class, the variance of that class, so forth. As many classes as you have. So these are the parameters of our generative model. And we're going to begin with a guess what those things are. So the E step is to complete the posterior probability. That is, to classify the data. Well, if I knew what these parameters are, look, I can now compute the probability of being class 1 given my data and this theta. Right? So if I knew the prior probability of each class, the mean of each class, the variance of each class, now I can compute this, y. I can compute the posterior. I can label my data because this is equal to my likelihood times the prior probability divided by my marginal. So if you had the data labeled, you could compute the posterior probability. Now, in the M step is that you now labeled your data. Go back and maximize the likelihood of observing the data that you actually observed. So the M step is a maximum likelihood step. Re-estimate parameters data. So look, let's go back through it again. So if I had my data labeled, I could compute the mean and variance of the data, my mixture model. And my mixture model says the data was generated by a mixture of normal distributions. So if I had the data labeled, I could tell you what the mean and the variance of each class is. What EM does is to say, in step 0, make a guess about the parameters of your generative model, your likelihood. In the E step, label your data based on the guess that you had. In the M step, re-estimate the parameters that generated your model, which is what you're doing is to maximizing the likelihood of observing your data after you have labeled it. So what we are maximizing in the M step is the probability of our data given the parameter, which is the maximum likelihood problem. So if you step back and think about what does EM do, in the first step is to say, let's use Bayes' formulation to find the posterior probabilities of your classes. That's your label. And the second step says, if those are your labels, let's use maximum likelihood to optimize the parameters that generated your data. Then once you have the distribution, once you have theta from the M step, you go back to the E step and say, all right, that's the mean and variance of each one of my classes. Let's relabel the data using the Bayes formula. And then once you've relabeled the data, you once again use maximum likelihood to find the parameters of your distributions. You go back and forth. All right, so what's this M step doing is the typical maximum likelihood. So the log of P of this is the log of the individual So that's likelihood. So as we will see when we explore EM, this likelihood model, maximizing the likelihood model, is what we've been doing in a number of examples before. So we want to find the derivative of our likelihood with respect to these parameters and find the parameters that after the data has been labeled, we can describe the best likelihood that we have. That's the basic story of EM. Now, you guys are you don't need to maximize this likelihood using any derivatives, because I just showed you, how to do it, which is here. If you had the data labeled, here's the path that you need to find the best mean and the best variance. That's just the maximum likelihood estimate of the mean and the variance for your data. And that's what you're going to use for the that image that you have. So image that you have describes some P of X. You have some density of voxels. Assume that there are 3 classes. Based on those 3 classes, make a guess about the mean and variance of each of those classes. That's your theta. Label your data based on that guess. That's your probability of Z. Go back and re-estimate the mean and variance of the classes that you started with. And you iterate this, and that's how you classify your data. Okay? All right. We're going to have a short class today because my student is getting an award upstairs. I'm going to go listen to him talk. Are you guys okay? Do you have any questions? Yeah.
So in the end, we will have the maximum likelihood estimation for the parameters and maximum posterior for the classes.
Yeah. Given those parameters, yeah.
Did you say n was the sum of nj or the number of data points?
Little n is the
Big N.
yeah. Oh, the big N is the number of data points. Yeah. It's if you look at the way we described number of data points that belong to class in k-means, it's exactly the same, except now you're summing the probability of belonging to that class rather than the hard labels. So oftentimes people start with k-means. That's how they get the parameters for their guess, and then they use EM. Okay. All right, guys.